that came before Cali or backtrack? Yes. I'm sorry, what was it? Yes.
And there's an optics STD.
Yep, there's IWAX.
There you are. All right, I'm just going to start. I think 2 CactusCons ago, I did a presentation that had no slide deck, no presentation at all. I just did it all in Terminal. That might have made it kind of dry, but I'm going to do the same thing. But this time, I actually have a slide deck. It's just still all in Terminal. So, I mean, dude, yeah, there's even like color and fucking animations. All right, so the about me and why you should care. I see this slide a lot, and I don't know, I just think like if you have a proof of concept, the rest of it doesn't matter. You should actually be just, you know, showing what this talk is about, and that's what I want to do here. So like, I don't matter, school doesn't matter for me, the company I'm at isn't relevant to this, the talks I've given before aren't relevant, these are all fake in this thing. Just trying to make a point like, this stands alone and there's proof of concepts. So, I know the description I gave for this talk was kind of vague. It doesn't really mean a whole lot. And that's because the concept I'm going to talk about is kind of vague. But what I'm going to talk about is meaning, context, and data. And the examples you'll see is involving TCP/IP and some machine code. And I would say assembly, but really most of it's going to be at the machine code level. So this is the formula. When talking about looking at data, I would say 100% you can't say what data means unless you have context, and that's what I've been harping on for so much. But this talk I'm going to kind of deter from that a little bit. I'm going to say that when looking at data without context, you can still have maybe a good idea of what the meaning is, just not 100%. And that's going to be the main idea of this talk when I'm talking about packets and code. So we'll still try to avoid large amounts of apophenia. So the question, this is data, like what is this, right? And it can mean a lot of different things. So by looking at patterns, you know, we have 13 ones, 19 zeros. In hex, it's 550328 5D. Is it ASCII? I mean, that's a couple symbols. The dot there is not printable, that's the hex 03, so maybe it's not ASCII. Is it two byte values, like port numbers? I mean, do these port numbers mean anything to you guys? And not really common ones, so maybe not ports. Base 64 looks like that. Is it base 64? I don't know. If you looked at the first 3 bytes and considered a color, it's kind of a dark purple. If we interpret it as x86 code, it's push EBP, add EBP, or add the memory location of it. That's the address in the EAX is forward to EBP, and then pop EBP. For anybody that knows assembly, does anybody know whether this kind of makes sense or not? I mean, the cool thing is that we're doing operations on EBP every time, right? Show of hands, is anybody really familiar with assembly? I just see a couple of those. So I'd say that this actually, even though it looks like there's a consistent register down the line, I would still say it's probably not valid assembly code because we're pushing this EBP register to the stack. And then we're doing an operation over here to the register, adding to it. But then we're just popping EBP from the stack back to, or the value back to EBP. So it's like that add really had no value. Like after we added it, we just overwrote EBP with its original value. So like that would also not make sense. And yeah, that machine code, the 5503285D, it would translate or disassemble, to that assembly. What if the whole thing's a number? Will it be like 1.4 billion? What if it's an epoch timestamp? So just take a look at that date. It's 2015, March 13th, default day, or default time, right? 1111. So I would argue that, like, again, to know 100% what this data means, you would have to know the context. But in the context of this talk, like an out-of-band context, this seems to be the value that might make the most sense right now, because that like string of binary is today's date. So now we'll move into some code golf. This is where we're going to get into packets, TCP/IP, to kind of try to apply that same kind of philosophy on a random string of data. So this is a PCAP file, like I would open up in Wireshark, but I want to try to do this whole thing in terminal. So that's a PCAP, that whole thing. That's actually a full PCAP. It's one packet, including the headers of the PCAP format. So let's look for some patterns. Our main goal is to get IPv4 to see if just random data is IPv4. So one way we could look at it, and I would argue this is not the best way to do it because of false positives, but we see this 4.5 there that I have highlighted in red. Is that visible? Okay, good. So I'll get into why that's significant in a couple of slides, but that would indicate that that part of the packet is indicating that it's IPv4 and a 20-byte header. But I mean, we could also echo a bunch of capital E's into a legit .pcap, and that kind of algorithm would say that we have 12 packets. So that doesn't really work for us. We could also look at the link layer before it. So you have your 2 MAC addresses, and then you have a 2-byte field at the very end of it that would specify what protocol is to follow, and the 0800 would indicate IPv4. But not every link layer is that way. Like a good example on wireshark.org, they have a couple captures, and there's the VNC sample.pcap, and it has like the null loopback, which doesn't use that format. We actually have this 4-byte value preceding 4.5 that doesn't follow that format, so we can't use that. So we'll look at a more intelligent way to go about that. I highlighted the 4.5, and I also highlighted that 5830. That is the checksum. So a little bit about IPv, or just IP checksums. The way to calculate it is you break out the 20-byte header. In this case, we're dealing with 20-byte headers, and I'll get to that in a second too, but we break it apart into 2-byte values. And I also zeroed out the checksum so we can do the calculation. We add them all up. So when we add all those values up in hex, we get that value in green. And we still need to have a 2-byte value. So we take that remainder, or the overflow, that 2, and we add it back into the end. So now that D turns into an F. And then we subtract the value we get from FF, or do a ones complement, and then we get 5830, which is the checksum. So that kind of gives us a way to, with an algorithm like that, if we look at a random stream of data, we see a 4.5, then we can look at what should be the checksum to see if it actually matches up with what should be the checksum if you calculate it. So for the 4.5, what does that mean? The 4 is what version of IP, in this case is 4. The 5, if you multiply that value by 4, that's how many bytes the IP header length should be. So that'd be 20. There's some math. So other valid values can be 4.5, 4.6, 4.7, like all the way to 4F. Definitely not 4.4, 4.3, or lower than that, because you definitely need 20 bytes worth of stuff to have a full header for IP. But yeah, an interesting question is, what are the chances that by dumb luck we could get the right checksum? And I mean, really, that's 1 in 65,536. That's not really a hard question. So, I mean, there is a chance that we would have false positives, which is why I would say that you can't be 100% sure with just data and no context that you have meaning, but a pretty good chance. And the thing is, if you have like a really, really small amount of data and you're seeing a lot of times that it's matching, then you have a lot higher confidence that it is IPv4. And another thing is, if we are looking for, our algorithm is looking for 4.6 through 4F, the problem is in real life, I see that a lot less frequently than 1 in 65,000 and on. So that would actually have more false positives than real matches. So I don't look at that at all. And actually, before I get to code, POC. So I want to say I have it in here. So I'm going to run that against my mystery PCAP. And what I'm getting here is the lower fidelity one. That's actually checking as if I was looking at the 4.6 through 4F as well. But the first one, the higher fidelity, is how many, the last number, the 8, is how many 4.5s it finds, and the 4 is how many of them would the checksum match. And 4 is actually a very high value out of 8 for that. I mean, you're going to have capital E's in your payload, so that's not really that weird. And just to do some validation here, if I did a TCP dump, and let's not do DNS, I'm not even connected to the internet, we will read in mystery.pcap, and I'm going to do it in quiet mode. So there's 4 packets. I mean, it's pretty accurate. And we'll get to it later why we get that 8 number. All right. So now let's do that with code. Here's some data. And now we're going to start looking at this as if it were executable. Like the question is this executable or not? So let's just disassemble it, pretend it is. So these are instructions here, but kind of peculiar, right? You have a couple conditional jumps, jump if not below, jump if 0. But the thing is, like, push doesn't set the carry flag, out S doesn't set the 0 flag. So like, why would you do a conditional jump based on a condition you didn't even try to set? You know, so I'd say that this is not code. What if we ran this command? We just echo all that data out to XXD to reverse it to make it so it's ASCII. That's what it actually is. It literally says this is not code. So when we're doing this kind of analysis, how low do we need to get? How low level do we need to get to decide whether this is executable code? Like a high level language like Python or C#, going lower, C, going lower, assembly, still not low level enough. Machine code, that's how low level we get. So the reason that assembly is kind of a challenge that way is I'm saying like kind of a random stream of data in the middle of anything, like in a packet or whatever. You're not guaranteed to be able to be starting at an offset that makes sense. So you could be starting in the middle of an instruction and then everything's going to be off. And to illustrate that, here's a stream of data that actually is code. We break this apart, and these are our instructions. So we got a couple moves, an OR, a couple ORs actually, an add, and not an instruction at all. So that's what that looks like. Let's kind of unpack that or repack that. And say hypothetically we delete those first 4 bytes, bring it back, and we disassemble that. Something completely different. We have 4 moves, a jump, and a pop. And notice this code starts to make a little bit more sense. Like we're operating on the same register in this case. And this is actually from real shell code too. From Smashing the Stack for Fun and Profit, their POC. So yeah, the offset and alignment, it actually really matters. So it's a lot easier for me to analyze at a machine code level than assembly. So what kind of patterns do we look for? There definitely are a lot of patterns that you'll run into when you're looking at assembly code when you disassemble it. I think one of the most logical ones is that whole compare or conditional check and then a conditional jump. So if I see a conditional jump, I kind of want to see a compare or a test before it. And there are a lot of other instructions that can set a flag, but like that whole 65,536 thing with the packets, those other instructions that set the conditions don't happen often enough to be a good heuristic. So to look for a conditional jump and you don't see a compare or you don't see a test for it, there is a high probability that it is not actually valid assembly code or x86 executable code. Yeah, and that's another complication. If we want to look for 2 opcodes in machine code back to back, like a compare and then a conditional jump, we'd also have to know how many bytes is a compare, right? And that's not the same, even for the same actual hex opcode. So it'd be nice if you could say like every XOR with EAX would be a 35, and it's always a 32-bit value. And in the case of the 35, that is the case. But as far as just XOR alone, those are all the opcodes in machine code that it could be. And we'll look at the 3.0 version of it real quick here. The 3.0 means it's XOR, and then the first operand is either a register or a memory location. And then the second operand has to be register, so not a memory location. And I mean, they can go, like there's the 3.1 that is the other way around. So yeah. So is it 2 bytes? We have this actual valid machine code and this assembly code that represents it. Yeah, they're the same. So you're XORing AL with what's in EAX. So 2 bytes. Is it 3 bytes? It's also valid assembly right there. Is it 6 bytes? A different 3 bytes, different format. 3 bytes that could be 2 bytes because we're using the SIB byte here, but this is one of those SIB bytes that doesn't actually mean anything. When you use this SIB byte with that value in the SIB byte, it actually makes it so none of the crazy addressing is done. This is a standard 2-byte version of it. Or with Rex prefixes, I mean, again, we're 3 bytes, that could be 2 bytes. So we have to like enumerate all these possibilities, and there are many. So we'll go through a couple of heuristics. Yeah, the conditional jump one, kind of went over that, testing for a condition. We should see a compare or a jump before it. When XORing, so yeah, this is a really good one. I like this one. We don't really move 0 to a register. We typically, because moving a 0 to a register, especially a 32-bit 32-bit register, it's like a 5-byte instruction. So XORing a register with itself happens to be 2 bytes of code and does exactly the same thing. So yeah, to compare, that's moving 0 to EAX, and that's moving or XORing EAX with EAX, which is just 31C0. As far as calls and rets, like a lot of you are probably familiar with subroutines. If you do any kind of coding, you kind of like call your subroutine. For this in assembly, you do a call, and then once you do your stuff in your subroutine, you can return from it. So the thing with this, when I'm analyzing machine code, is if I'm seeing more returns than calls, something's kind of weird. You kind of expect to call a subroutine and return from it at least an equal amount of times that you called it. So if you see a lot more returns, that's one other thing to say this might not be code. And also, this is not really, this might be more compiler specific, but I also notice that there's a lot of pops before returns. And it makes sense, but you don't have to have that. This is one of my favorites, and this is definitely at a machine code level. This is not really a kind of an assembly thing. Is unlikely machine code. Machine code that a compiler would never do, and I really find that interesting. And these are 3 different things that I'll go into real quick here. So you have these 2 versions of XOR. You have the 3.0 and the 3.2. And you'll notice that the operands for this first one, you can have a register, a memory location, and then a register. For the second one, you can have a register only, or the next one could be a register or a memory location. But for both of those, you could encode it as a register and a register for the first one, and for the second one, you could also encode it as a register and a register. So you can actually do the same exact thing in assembly, but with different machine code. And if you're compiling some assembly or assembling some assembly that says XOR AL with AL, the compiler or the assembler has to choose one of them. You can't choose both. So one of them is not going to be picked. So it's machine code you should never see. And if I see that often, then I could also assert maybe this isn't actual code. The SIB byte, kind of talked about that, but there is a value for the SIB byte that you should never see because it's not useful. So those 2 different versions of machine code, XORing AL to the value that's in EAX, those 2 different pieces of machine code do the exact same thing, and a compiler will do the second one. And then my Redundosaurus Rex slide here. So there's the Rex prefix. It allows you to access 64-bit values or register values. So the R8 register, you would have to put a prefix in front of your instruction in order to access registers that are only for 30 or 64-bit processors. So adding that 4.1 in front of our 3.0C0 instruction allows us to access R8B. And that's like a normal use of it. That's actually a valid way to do that. But notice that all 5 of these instructions are XOR AL with AL down the line. So, with the 4.0, 4.2, 4.8, 4.8, we have some redundancies. So we should see 3.0C0 if we're looking for XOR AL with AL, but we should never see those other 4. So if we see those other 4, we're probably also not dealing with in x86 code. So on the POC side, I decided to test about 500 sample files, half of them code, half of them not. I try to get as various as I could, so both Linux and Windows, x86 and 64. For the code side of it, for the non-code, I just have a list of all the different file formats, about 10 of each, just to get some variety there. And with the results of my testing, all the yellow there is pretty much the non-code, right? And this is like a frequency count, so how many times I see, in this heuristic specifically, the XORing a register with itself, I'm seeing that happen like, that low amount of times in non-code. In code, I see it like this. It's kind of all over the place, but always higher than non-code. So it's kind of, it's reliable and scriptable too. So then we'll look at I'm not gonna go through all the heuristics, but another heuristic here is the test and conditional jump, and just test, not compare conditional jump, but test and conditional jump. it's not as reliable. But the thing is, if I mix and match all these heuristics, I can correlate them and get a really reliable result. Before I get to that, I'll do some POC. I think I'm running really quick. That's okay. So, actually, yeah, I'll probably spend some time on this POC just because it's kind of fun. So the script that I wrote it in Lua. Lua is absolutely not my favorite language, but there was a specific reason I did it for this, which I'll get to. But trying to think of what kind of code I want to run against this. First, I'll start my script here, mchecker. And I don't know, what's the typical binary package on OS X? Anybody want to throw something out there? Bash. Wait, would that be in user bin? Yeah. Okay. I thought it was in just bin, right? We'll do bin. How big is bash? Okay. So I did a metric, like I correlated them all together and did kind of a metric, just one single number. And it's anywhere from like -10 to +10 in general. Like 0 is kind of ambiguous. Like if I get a 0, like I'm probably gonna want to inspect it myself. But it's like kind of stupid easy. You don't have to like actually analyze a bunch of stuff. Like my script here says it's likely code, you know. And you can get a little bit crazier with this too. So I'm gonna do well. First of all, let's see what I got here. I think I had yeah, let's call it slices. I'm just gonna remove, yeah, screw it, let's remove everything in here. Cool. So what I was saying is like a random stream of data. It's not really, I'm not really proving a whole lot by analyzing the whole executable. I mean, my script could be cheating and looking at like the elf header and being like, oh yeah, it's code because it has elf. So I'm gonna take a random slice, just a small little chunk out of an executable and analyze that. And I think that's a lot cooler. And I'm definitely not gonna get like as high as like an 8.1 or whatever, or I may, I don't know. But it's a cool challenge. So I'm gonna use DD and going to do an input file of this. I have been using Nano as a test, but I could use something else if anybody wants to challenge that. I don't care. LS, all right. So pretty sure that's in bin as well. And then OF, I'm going to call it LS slice, or just double up on that S. And I'm going to set the count to 1. I'm going to set the block size to just 2K. We're only going to take a 2K little snapshot off of this. And then we'll skip some, like some of the little 2K chunks into it. So what number should I put in there? Like anywhere from like, 1 to 50-ish or whatever. I'm looking at you now because you're 42. Okay, 42 is good. Okay, so wait, maybe I didn't type that right because it only got, no, it says literally 0 bytes transferred. I don't trust that. Oh yeah, so we'd have to probably pick a lower number because LS is probably really, really small. I'm thinking, actually, 34. Yeah, no, I think 42 is too high for that. So let's just do a lower number. 4. Okay, 4. Yeah, there we go. Okay, so. Oh yeah, God, man, it seems like muscle memory on that. So yeah, it's a 2K file. So now I'm going to do I don't actually have an alias right now, and then I'm going to do my ls slice. So it's still saying it's code, but I mean that maybe still doesn't prove anything to anybody because maybe you want to see non-code. Okay, yeah, sure. Well. Maybe I should just do the whole password file because it's not a very big file. Well, I mean, let's check. So that one, right? It's like 5K. Let's do the whole thing. Okay. Not code. Yeah. So yeah, another really, really interesting thing. This I love this part. Okay, so I'm gonna do my other script in my favorite language, but I'm gonna go back to my. Actually, no. So you already saw that. Like for that mystery PCAP, it said the 4 out of 8 thing. So let's do mchecker against it. That's fine. Okay. So anybody want to guess why that could possibly be? It is right. It is right. Someone. What's that? Yeah. And it's not anything unusual either. It was this PCAP that I have was a legitimate PCAP that I made. The traffic that I captured was me running netcat to transfer an executable file. So if I do a hex dump of that, I hope this doesn't like look shit on here, but it does. What's up? Oh yeah. Oh, okay, wait. And 15? 15? 16. 15. I'll do 8 because 8's lead. There we go. So the thing is, yeah, in fact, you know what a better tool is? TCP dump. Or yeah, I should say that I'm reading from it. And I would do -X, that's my favorite, but I'm going to do it -A just to fit into the screen properly. So that last thing there is one of the packets. That's just one of the 4 packets. So you notice you have the ELF, and then you have the rest of the stuff, which is non-printable characters. But that's the point. Like one packet, I'm transferring a very small executable. So it's cool. Like the whole point is that this script, it's not looking for headers or anything like that. It's looking for patterns in just the bytes. It's looking for machine code patterns. And I'm probably going to finish in record time. This could have been lightning round, but I'd rather finish quick than go over. So I'll get back to my actual presentation. Unless you want to see more examples with this. Like I did the non-code, but if anybody wants to see some more crap, whatever, I'll get back to it. But I'm going to reattach to my presentation. So the reason I did Lua is Suricata, you can actually do Lua within the rules themselves. So it's cool that you can do string matches. It's cool that you can do PCRE. I love regex, but you can also do scripting as well. This is one thing that shamefully I don't have a POC for, but it should be straightforward. You need like this little thing in the beginning of your Lua script to just kind of import all the values from Suricata. And then you have your main function that does the matching. So this would be the brunt of all my mchecker code. And then you just add this little line into your IDS signature. So in this case, this signature, it's a real signature except for the red part I added in there. What's up? Well, yeah, it's snort, which you can also use on Suricata as well. But yeah, this is snort rule. And it's specifically looking for shellcode. I kind of like this rule, even though it's false positive as hell. But it's looking for hex E8, 4 nulls, and then a 5/8. So that E8 in the machine code for E8, what it translates to in assembly is a call. And the 32-bit value that follows it is what offset to call to, how far to call to, like the address of where you're wanting to call. So it's kind of strange. We're doing a call and then it's just null. What that means is you're doing a call to the very next instruction after it, which kind of is nonsensical. I mean, why not just do a no-op, right? But what this allows us to do, because of how a call works, when you do a call, the return has to know where to come back from, and the way that it handles that is pushing the value of EIP to the stack. So now we have EIP on the stack on our very next instruction. The 5/8 is a pop. It's actually pop for EAX. So when in general you're not allowed to directly get the value of EIP, this code sequence allows us to get EIP into EAX, which is kind of a cool little hack, and there's a signature that looks for it. And often it finds it in things that is not code. So like if 99% of the time you have a signature looking for what should be shellcode and it's not even code in the first place, false positive, then why should you even analyze it? Why look around all the other stuff? It would be nice if it just never triggered in the first place. So you can do some scripting, and in my case with Lua, to just eliminate that from even showing up as an alert. And then you can only analyze the ones that happen to be code. And on a personal level, the only time I've ever seen it be code, it was like, I think, Adobe Shockwave. And sure shit, they use this code sequence for whatever reason. And that is all I got. Short talk, you guys. Like, have a little break. And questions. Also, this slide deck software, I'll get to you, Andrew. But yeah, the slide deck software is something I did homebrew, so it's on my GitHub. If anybody wants to use this atrocious thing, this will probably be my last time using it, but it was a fun experiment. I called it unimpress.pl because one of my favorite frameworks for slide decks is impress.js, which is, it's all a web thing, but I just wanted to be unimpressive and do it all in a terminal. But yeah, Andrew. It's a bug. See, watch this, 113, 114. Yeah, it's the same thing. One cool feature about this though is like I don't know, it might be subtle, but or if it doesn't even show up. Oh, darn. I'm gonna resize this real quick just so it can be seen. This isn't at all about the presentation itself, and it does actually readjust. So some of the stuff is gonna float off of the screen, but that little sidebar actually correlates from how far into the slide deck you are. I didn't notice that it wasn't showing up, but I kind of, it's like something that I kind of wished I could see in other presentations just to kind of get an idea of how far into it we are. Yeah. And I'll just kind of cruise all the way down to the end here. Make this big again, just so it can be on that screen. It's open source, man. Along with other stuff, like that Lewis script is up on my GitHub. I have a blog where I talk about all over the place how assembly is too high level, maybe how, regex is too high level, or, because I go into the compiler side of it. Also, not on my blog, but I just submitted an article to POC or Get the Fuck Out on how Scapy is too high level. So it's talking about how you can make a packet or a PCAP with just XXD and echo. So I'm all into like how everything low level is too low level. So any other questions? Joe?
So you're like that guy who they make fun of on television. It's like, I wrote the program with binary.
Yeah, so for one, I am that guy because also on my GitHub, I have this other little script called M to ELF that you can, in a text editor, type in hex and you can convert it to an ELF packaged executable. So you can program in hex, but I also made it support binary too. So I am that guy because I have wrote programs in binary. Good question. Yeah, you, Eric. Yeah, I mean, I do see it. So I think the point of that, a couple points of that, if I'm just running the script standalone and not part of an IDS, if I see something that is ambiguous, like around the 0 range, to me, that's just a signal of maybe I should look at this with my own eyes, because there's a lot more patterns that you can just kind of see. Like some of them are kind of hard to do automated. Like you still could, but they're just harder. One of the big things I would look at is like if you're operating on the same register over and over and over again, like, in a straight line, that's kind of indicative of code. Not really, but I mean more than just random stuff. And as far as on the level of automating it through IDS, I would just kind of be careful about the threshold. So, in that case, false positives are okay. Maybe have stuff that come in, be alerted on that might not be code, but still a better chance of just completely not being code. You could at least eliminate all that. That's at least how I would tune it if I worked that out. Dre and Jim. No, but I'd love to try. And I mean, really, I suspect that if my heuristics don't work well, there's this methodology would still work well, because say your script, and were you here for the whole Okay, cool. So when I was talking about the conditional checking and the conditional jumping, like if you want to do conditional jump, you might be able to find a way to not do that by testing a condition before it, but that's kind of like crazy, right? I mean, yeah, with self-modifying code, you might be able to do that, but in that, you're probably going to have a problem of still doing, conditional stuff just to set that up in the first place. And that's not the only heuristic that I do. So, I mean, maybe you don't use XOR with a register with itself to set something to 0, but like these are all things I check for, and it's incredibly extensible. I mean, I only have like a handful of heuristics, so it's checking not for patterns of malicious code. It's checking for patterns that necessarily have to exist in code. Yeah. So we can get together and like if you have samples, I'd love to check it out. Okay. Cool. Jim? So I think the only time I've had, and it'd be hard to call it a false positive or false negative, it was like almost like the value was literally 0, was that Adobe Shockwave thing. So that was the one. So when I was talking about the 500 samples I went against, the code and non-code, 0 false positives, 0 false negatives. Every single one that was code, the script said it was code. Every single one that wasn't code, every single time it said it was not code. It's pretty well tuned. I mean, there's a chance that it could be, you could get the false positive or false negative, but again, if that's the case, it's going to be just by a little margin, and that's when, like, if you're running this manually, then you inspect it yourself. If you're running it automatically, then just adjust the threshold to where, like, even -3 could be considered possibly code, if you want to be careful about it.
Do you have any plans for adapting your technology to work on interpreted languages such as Java or ActionScript?
No. So like, would we be checking for the difference between just like a text file and code?
I mean, code is code, but like, if you could detect a Java file over the wire,
yeah,
you know it's an actual Java file, and you know it's I don't know.
Like the bytecode of it?
Yeah, this looks like they're using reflection here. Since most people don't use reflection and only exploits use reflection, I should flag this.
Yeah, somebody else can do that. Or that could just be a one-off IDS signature or something. I don't know. That, and I'm like completely not familiar with Java's bytecode and how they do it. Like, this is very x86 specific. More questions? I'm totally open to questions because I was totally short on time. No, I haven't as a test, but I mean, well, yeah, just little parts of it, like, yeah, and it, in theory, it would work. I mean, like I said, the level that, I'm not using like some library to disassemble or anything, I'm just byte by byte, so in theory, it should work just like this. I mean, it's the fact that I'm looking at a file is kind of irrelevant, especially with like what I did with DD. I just cut a little slice of in data, not even a file, So like, as long as it's looking at data, it's going to interpret it like anything else. And if there's code in there, it's probably going to detect if there's code in there. Yeah. Sort of. I don't know. I have this thing where, like, when I research something before giving a talk, I spend 5 minutes, and I can't find it, I just do it myself. It's probably a terrible philosophy, but I didn't find anything that does something like this. But I mean, community's getting bigger, so I might have duplicated efforts, but this is my style on it. and in particular, like, if somebody did do it, I would imagine that they probably didn't do it in Lua, and I would say that there is an advantage of doing it in Lua because of IDS. This can be like almost dropped right in IDS rules that look for shellcode. So people that are analyzing alerts only have to analyze alerts that are actually code. Because, like I'm saying, in the wild, like the false positives on those kind of shellcode rules, at least the ones you see. I mean, yeah, the ones that are good, you don't see the alerts on it, but the ones that are bad, you see, like, no joke, 99% false positives. So the thing is, none of them are code in the first place. So if you can just automatically just cut that off the top, it's, yeah, a lot more accurate. Yeah, Rex?
Have you, just out of curiosity, have you run against JPEGs and other formats to see the likelihood?
Thank you for asking. let's do it. And I have, but I just grabbed a sample of a bunch of things off the internet, and I did have that slide that had the list of files and JPEGs were on it. So I'm gonna oh yeah, it's relative. Okay, so those are the different file formats that I have. You still want to do JPEG, or you want to pick a different one from here? Zip. Zip's kind of a weird one. Like they all work great, but Zip's kind of a weird one because all they are just is zips of all the other ones that I put in there. But I can do Zip. So I prefer that. Well, no, like so the reason I like the idea of SNES is because it is code, right? It is code, but it's for a completely different architecture. So in the case of this, it's going to fail. It's not going to look like code because I'm saying that the script that I made looks for x86 code. And this is just a random sampling of, I don't even know if I've played any one of those. Tekken 2 maybe. Anybody see his workshop? Yeah. Cheater. Okay, so I'm going to do mchecker, samples. Why do I keep on doing it from root? Okay, SNES, and which game out of that list of about 10 or 11?
All I can see is
What?
It's just off on the left-hand side.
Okay,
Tekken.
I'll do Tekken. Cool. This might take a little bit longer because it's larger, and I mean I can strip down some of the heuristics in it as well, like more of the higher fidelity ones. Also, I have a lot of logic going on it that I'm not ambiguous. Maybe non-code, which is still accurate for x86. But yeah, so a couple things I didn't show you. If you want to look under the hood of some of the stuff it's doing, and I'll scroll up when it's finished. But yeah, cool. Oh, I'm scrolling right now. You're not gonna. Oh wait, you're saying that it. Yeah. Okay. Gotcha. Oh, come on. Oh, I know. I'm gonna get it. I'm just resizing this so it's somewhat big. Yeah. Cool. Cool. So I'll scroll up again. So like if you don't necessarily trust or believe what the output is and you kind of want to know why it's determining that, it counts all the instances of a register with its, like XORing a register with its own register, and it itemizes it based on the A register or the B register or whatever. And you should expect more of one register than other ones. Like if you see it's like an even amount of each register down the line, you might be dealing with random data because you're going to have these sequences hit by dumb luck. So if you see like entropy is really, really high, this probably also isn't x86 code, which is why I also look for entropy as well. I don't know if it cut it off on the screen, but I also count like a byte frequency. So, I count all the nulls, and in it I say it's a null or it could be an add, but more often than not it's a null. And it just gives you a frequency of all the instructions that if interpreted as an x86 instruction, what that instruction would actually be. So if you're used to what kind of patterns that should be, you can kind of call out like whether that looks normal or not. And you can kind of see some patterns in that. I also happen to count things like down here, if you see a CD80, you see a high frequency of those in a very small size, like 500 bytes or so, or 300 bytes. If you're looking at 300 bytes and you see like 8 CD80s, you're probably dealing with Linux shellcode. And I try to count for int21s as well, but I'm shit for Windows shellcode. The calls versus the rets, the pops versus rets, how many jumps, conditional jumps with tests there are, how many conditional jumps with compares there are. Oh yeah, no, I didn't really go into this heuristic, but unlikely fences, there's a redundant fence instructions that should never occur as well. Even the Intel manual specifies that there's like these fencing or fence instructions that should never happen. And then the unlikely mod RM heuristic, the SIB byte that you should never see, and then the redundantosaurus rex stuff you got going on there. Cool. So we did not a JPEG, we did a SNES file. Yeah.
long sequence of
Oh yeah, like breakpoints, you mean?
Yeah.
Yeah.
So,
I haven't added it, but yeah.
On Windows, the binary, depending on the compiler, I know Microsoft Visual Studio, what it'll do is in order to align functions, it adds the function regions with entries.
Something I could.
CC bytes.
Yeah, CC.
So if you
Well,
saw a bunch of CC bytes, you probably, and it's an EXE, it's probably
so would it literally be a CC or would it be a CDO3?
CC.
CC.
Single bytes.
Okay.
You don't use CDO.
Cool. Any other? Yeah. Aaron, and then.
Last summer, I was responsible for sharing those machines that and I ran into a number of instances where there were files with like gif headers, but binary code inside of it.
Yeah.
And to make it very interested, I kind of large sample that for a while and I to
Okay. Okay. Yeah. No, I would like to see that because I would. In theory, I'd say it would match because it's not looking at the headers; it's looking at the patterns and the data. So yeah. Cool. Rex, do you have a question? I saw you too.
Have you, maybe it's another project to do, but have you ever thought about trying to find some methodology instead of graphical steganography?
Stego, yeah. I mean, there's like Snow. I think is one that already exists for. And yeah, Snow. I think it's Snow, but regardless of what it's called, it doesn't matter. The trick that they use is they have what would be redundant types of instructions, and they'll swap them out. Like they'll just do a kind of a find and replace to inject the data, but the code does the same thing. It's the same amount of data. And, I mean, there's ways to detect it kind of too with heuristics, but yeah, it's definitely that is a form of Stego. And yeah, you. So I'm not like an expert on this, but when we're talking about the code in PDF, it's not x86 though, is it? Because I don't think it is, and so at least my code would fail to recognize code in a PDF if it's not. I mean, like maybe it's JavaScript or something like that, or. Yeah, and I mean if it's like in plain in the like not packed or not encoded or whatever, it's just plain x86 code, it would, but I wouldn't. I'm not sure or certain that would be a thing for PDFs. Haven't tested it, so I wouldn't say anything on that.
Many PDF exploits will use JavaScript to decode a payload so it'll be obfuscated first.
So it wouldn't work, yeah. Unless you looked at the memory.
Let's look at the memory.
Yeah. Anything else? This is awesome, man. Like I'm actually like 2 minutes away from my slotted time when I finished 20 minutes early. So I love you guys. Yeah. That's true. Oh. Wait, did you say that, Andrew? Is it 0? I mean, I don't know what your clock says, but. But fine, you're organizing this stuff, so.